In this video, I'm going to be working AP Pre-Cal Homework 11.1, and we're going to be choosing which model is correct for a given context, and also running regressions on certain types of models. I think some of which you can see in the list right here. But first, we're just going to pick which model is right. And so, I'm thinking for linear, that's kind of like a constant rate of change, like each thing costs some amount or something like that. Piecewise linear is going to be where, we have maybe two different amounts, but it's like, two different contexts smushed together into one. I mean, we have that, what do we have? Five and okay, well, I've got five answer choices, so even if they're not labeled A, B, C, D, and E, that's why we'll see one of each. Quadratic is when we see increase and then decrease, or decrease and then increase. Exponential would be increasing at an increasing rate, and logarithmic would be, in general, increasing at a decreasing rate. All right, so a car traveling on highway speeds up to pass another car, then returns to its original speed. I think that could be piecewise linear or quadratic. I'm going to come back to that one and relabel those. Okay, during a drag race, car starts from rest, quickly gains speed, then continues to increase its speed more slowly. Okay, so the speed is increasing at a decreasing rate. That's going to be logarithmic E. Okay, a rocket-propelled car starts from a stop and continues to accelerate. Okay, so continues to accelerate. The velocity continues to increase. That's going to be exponential because it's just the velocity is increasing at an increasing rate, or the height of, or the distance from the start is just going to be increasing at an increasing rate. And all right, car approaches a stoplight and applies its brakes and slows down at a consistent rate until it stops. I think that sounds linear to me. Okay, you could definitely make the argument that it was piecewise linear, that after it stopped, it would be at speed zero. But let's keep looking and maybe we can adjust our answer if necessary. Car on a highway travels exactly at the speed limit, then is forced to slow down and travel at a lower speed limit when entering a work zone. That seems piecewise linear to me. That's like two different speeds. And then, so which one do we not use? Quadratic, okay, yeah, up and then down. Yeah, don't think about it too much. Up and then down, that's going to be quadratic. All right, for each of the following situations, determine whether a linear, quadratic, or cubic would be best used to model the situation. Okay, yeah, and then these are the ones that we, if you were working off the notes, these were off Mr. Passwater's notes, and so we're just going to do these again, though. Because really, I think it's just about the keywords. Each water balloon is roughly spherical, and the radius of each water balloon is measured relative to the amount of water, like volume. Okay, and so what's amount of water? That's going to be a volume. And what we know is, in general, volume, that's going to be kind of like a third degree measure, like a 3D measure. So we're going to want to look for a cubic polynomial. Okay. Totina's pizzas are on sale at the local grocery store. The price of one pizza varies between $1.99 and $2.19 depending on the variety of pizza. Okay, so the total number of pizzas are counted relative to the total price of the pizzas at the end. Okay, so this one would be like, you don't know exactly how many of each type, but you know that it's somewhere in there. That's going to be linear. Linear model, yeah. Each one costs approximately $2, right? If you're not that worried about the change and, it's not that much for each pizza, yeah, you think about it's about $2 each, and that's going to be linear. C, a sprinkler is placed in a yard to water the grass. Circular pattern waters all the grass. Okay, yeah, the radius is measured relative to there it is, area. Okay, and so area is kind of a two-dimensional measure, and so that means we're going to be looking for a quadratic. All right, now we're kind of getting into the part where we might need to use a calculator when we get these data sets. So we're going to start you off with just kind of a table without any kind of context attached to it, but we're going to a place where we're going to want to have a table that gives us data about a situation, and we're going to possibly draw some conclusions. So we're going to start by using the rates of change of f over the given subintervals to determine the function type that best models f. And so we're going to go all the way back to kind of the beginning of the course and look at the first difference, second difference, possibly even the third difference, looking for, where it's constant or approximately constant, and, basing our conclusion off of that. So first order difference from 5 to 18 is an increase of, oh, but wait a second, 0 to 2 is a width of 2, but then 3, 1, and 2. Hold on here. Okay, yes, I forgot that they can do that to us, that we need to think about the average rate of change. Okay, and that's going to be increased 13 when x increased 2, rise over run. And so here I increased by 6, where x increased by 3. Here I decreased by 2 when x increased by 1, and then decreased by 11 when x increased by 2. All right, and so that's going to be 6.5, 2, -2, -5.5. And then we look at the rates of change of those, but those are not over. Let me think about that. Okay, I think this may be beyond the scope of what we're asked to do in AP Pre-Cal, to look at a table like this and infer on the rates of change of the average rates of change. Maybe besides to say that they're clear, the average rates of change are clearly decreasing as I move left to right. Because if I go and kind of like think about the change from 6.5 to 2, which would be a decrease of 4.5. I'd be really running from 0 to 5 there. That data that I'm getting that's giving me that -4.5, that is taking data that originates from x equals 0 and goes all the way to x equals 5. And if I look at 2 to 6, so I guess I would probably need to divide that by 5. 2 to -2 is a decrease of 4, divided by 2 to 6 is an increase of 4. These are about 1. And what I'm saying is, okay, I decrease by 3.5, and 5 to 8 is 3. These blue numbers, these rates of change of the average rate of change, these are all approximately equal to -1. And so if I see constant second order differences, that's quadratic. And so this one's a little bit... this one's not perfect, but I think if we go and we look at it on the calculator, if the first thing we did was, rather than just like do the average rates of change, was, look at the scatter plot, we would probably see that it looks quadratic. Okay, so I go get the calculator and I go to stat, edit, because I need to edit the lists. Okay, I'm going to type in my x values first, 0, 2, 5, 6, 8. And then I'm going to go over to list 2 and type in my f values. Okay, then I will go to stat calculate a quadratic regression, or I can just choose 5. X list, list 1, Y list, list 2. We don't need to worry about frequency list. Maybe I will store my regression equation in Y1. We can get the Y's out of F4. So, oh goodness, I'm in polar mode. Okay, if that happens to you, you just hit that mode button, go over here and make sure we're in function mode for the, just can't really think of any situation where being in polar mode would be all that helpful in AP Pre-Cal, because they're kind of testing you on things that if they let you use a calculator on it, it wouldn't make that much sense. But I'm not saying it's impossible, and maybe I'm just not thinking of them quite yet. Okay, so I'm going back to stat calculate 5. Okay, I wanted to store that into Y1, and we can calculate. All right, and now it's giving us all this data. We should probably write it down. Okay, so there we go. We kind of copy down those numbers, ax squared plus bx plus c, and that's the equation of our model. Okay, we don't get the, maybe I need to turn the diagnostics on. Yeah, I barely even remember what that means. I did teach AP Stats one time a long time ago, and so R squared, that pretty much tells you how, hey, how good of a model is this? And if it's close to 1, then based on my memory of teaching AP Stats, that makes it a really good model. And 0.998 is going to mean that this is a very, very quadratic data set. So what would your model predict to be the location of the maximum value of the function over the interval probably 0 to 8, right? Again, you can't quite see that, but that's what it just says over the interval. I think we meant 0 to 8. So let's look on the calculator. Let's graph this thing. So let's zoom to the stat, because I think that'll mean that we're definitely trying to get those. No, that did not work like I'd hoped. Okay, now let's try zoom fit. Okay, that's even, no, that's one that people have a lot of luck with, and I never seem to have very good luck with. Okay, yeah, see, I don't love that, but it is showing us the maximum, so location of the maximum value of the function. Okay, so let's calculate the maximum for as x runs from 0 up to 8. Okay, great, give it a guess. 4.399. And y is 24.255. Okay, so that would be the predicted maximum. Okay, I'm going over here to the next one. Maybe I shouldn't have cleared the RAM if I wanted to keep the diagnostics on and kind of like just check myself. R squared is not really something that you need to know the like meaning of in AP Pre-Cal. It's something that you would get in AP Stats, but it's, I think it's actually something in Texas that we talk about in our Algebra 1 course when we do linear regression. So it's something you've heard of. And the next one, we're again using the rates of change over the subintervals to determine the function type. Okay, so 1 to 4 to 6 to 7 to 9. Okay, that's again not an even, like, not an even change in x's, which is kind of annoying, but that's all right. From 6 to 33 is an increase of 27. So the increase of 27 when x increased by 3, that would be 9. And I think I'm going to just come back and clean this up here in a second. 33 to 107 is going to be an increase of 74 over 2. 107 to 191 an increase. Oh, oops, I couldn't see that. There we go. An increase of 84 divided by 1. Then 191 to 613. Okay, well, whoops. Let's get over here and just 613 minus 191. All right, 422 divided by 2. So that's going to end up being 211. And I'm just going to leave that there. 74 divided by 2, that is 37. And this one was, I just completely, 9. Plus 9 there. Okay, and if I look at how this is increasing, 9 to 37 is an increase of 28. Then more than 28. I think, okay, I probably should go to like probably the third order. But I don't know about on one where the x's aren't evenly spaced. Let's look, because like this one I could say, okay, well, it's increasing at an increasing rate. Okay, the rates of change are increasing clearly as I move left to right on x. And so that would be, increasing at an increasing rate seems a whole lot like exponential. And so maybe what I should do here, rather than going to 3 orders of difference, is use the technology that I definitely have at my disposal and see which one works better. Alright, so I'm going to go over there and I'm going to calculate a cubic regression, which is option 6. And then I'm just going to scroll down and calculate. And okay, I did turn the diagnostic off. Let me try that again. Alright, so I got that turned on. I'm going to try that again. And I've got 0.9995. Okay, so I must be seeing. I'll go ahead and show that because that's part A here in a second. But might as well go ahead and just, kind of try out exponential regression and see what happens. Where is that? Must be down here. Yeah, it's option 0. And then I'm going to go down and calculate. And oh wow, that's an even better r squared. So I guess it is exponential. That's interesting. There's two different models that work really well. Without further context on the meaning of f of x, we would not have any way to say. But I like that bigger r squared, so I think I'm going to go with that. But that being said, that is not part of this course. Okay, so I'm going to just say increasing at an increasing rate, probably going to be exponential. Okay. I really like this f of x equals a times b to the x equation, so I'm going to say an equation that models f of x would be y equals 3.321, that's a, times b to the x, 1.784 to the x. Okay, and then use the model to predict the value of f of 5. I should have stored that regression equation into y1. So if you realize you didn't do that, you could call for the exact same command you just did by pressing second enter. And it would be okay, it wants me to do that. Oh, but actually it might not give me the option. I think I needed to push comma y1. But that's alright. I just go stat and calculate. I remember that was option 0. Fancy, store the regression equation into y1 and calculate. Alright, great. And now it's stored. Predict the value of f of 5. Okay, well, thanks for that. Okay, clear out. Yeah. And then call for y1, plug in 5, and it knows what you mean. It's whatever you let y1 equal over here, which included all the decimals, so we're going to get a more accurate answer. We're going to get 60.027. So f of 5 is approximately equal to y of 5, which we ran through the calculator and got equal to 60.027. Now the next one here is a new song which was released on Spotify. Total number of downloads on Spotify at time t days after release is given by the function n of t. N is thousands of downloads. Okay, and then we've got a table here. Sketch a scatter plot based on the shape of the data. Okay, this is something different. I think I wrote this one because I just don't know exactly what you need. But a lot of us are going forward into AP Stats next year. Maybe in addition to or instead of AP Calculus, and I want you to be kind of at an advantage in that class. So we're going to talk a little bit about the scatter plot. So I'm going to go in and edit the list. You need to watch me do that. Besides just maybe get there. So I'm going to go stat, edit the lists. I think we press, wait, what is it? Is that, yeah, you highlight the list, you press clear and down, and then it gets rid of all of the data. Alright, so we got those. If we want the stat plot, we go over here to the stat plot menu by pressing second to get at that thing right there. Plot one. Yeah, we're gonna just turn that on. X list, Y list, color blue. Wonderful. Okay, so we're going to. I think that was the missing piece when I was trying to zoom to the stats. Whoops. Let's just go all the way back out. Zoom to the stats, which would be 9. Okay, there's the picture of it. Oh, and we've still got some equation in y1 that is just still graphing, so I'm going to just ask it to stop graphing and clear that out because we will not be needing that anymore. Okay, there we go. We've got a picture of the scatter plot, and we can sketch that. Really what we're supposed to see is the shape of the data. So we've got, basically something like that, increasing at a decreasing rate, looks very logarithmic. Okay, so what function type would best model n of t? Well, that's going to be a log function. Use the model to estimate the number of downloads that occurred between t equals 10.5 and t equals 11. Okay, so I'm going to use a log regression. I guess we're going to need to write down a model if we're going to use it to estimate downloads between 10.5 and 11. So I think I'm going to go in and do a log regression. So I'm going to go stat, calculate, because that's where all the regressions are, okay? And I'm looking for a log regression. So I see a natural log regression, that's number 9. That's really the only one we got. I was wondering, like kind of what was the format of this going to be. And I think it's just got to be in terms of natural log. And that's great for me. So I'm going to calculate, store it in y1, okay, get a good r squared value. Okay, so I'm kind of confirmed in my suspicion that this was a logarithmic relationship. And I've got a plus b log x, natural log x. So y equals a, which is 3.744. Or actually, I might say 35 dot 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 plus, acknowledging the fact that I'm definitely using all the decimals here because my final answer is going to be some number of downloads, and I'm going to want to also use the graph to confirm my answer. Okay, so plus, think about that, b natural log x, 89.905. Natural log x. All right, so at time 10, t equals 10.5 and t equals 11. Okay, so what I'm kind of interested in is how many downloads had occurred at 10.5 days, and then how many downloads had occurred at 11 days, and what's the difference in those. And so I think probably y of 11, I'm going to report that, and y of 10.5. And then the difference, I will also do that. And, if you just saw it as the difference, like kind of from the beginning, you should just go for it. I'm going to put both of these up because I'm going to have a little bit more explanation on the graph for a question like this. So, get out to the main menu, and, okay, I stored that in y1, so I'm going to ask for y1 of 11. It would be 219,000, and that kind of makes sense if we look at it's a little bit bigger than 210 and definitely less than 240. Okay, so that was 219.327. And then at 10.5, I can just call for the same thing with second enter, or scrolling on this nice new interface, scrolling up by 1 and pressing enter. But if you're on a TI-83, you'd need to press second and enter. We do that 215.145, 215.145. The difference, if I, maybe I'll just demonstrate that, minus this number would be 4.182 thousand, so 4,182. Would be the number of downloads that occurred between those two times, to our estimate. And if we were to go over here and graph, 200, no, pardon me. Yeah, I guess that would be what we need to see, 219.145. And we looked at the graph here. See, okay, that log regression, it's going right through those data points, so that's a really good model. And then here we would need to zoom way in, but let's just make that window just right, and then maybe graph again, and then okay, we see our log model. We're really zoomed in here, but here we see those 2 points where that's going to be 10.5 right there, and this is going to be 11 if we ran the intersection. And so we're seeing that's the difference. If we take the difference in the two y values, how many downloads occurred between these two time periods, or between these two time points. And then if we wanted to determine when the total number of downloads surpassed 350,000, okay, we'd say, okay, when we want to know when is n equal to 350. So what we would do is probably go back to a more standard window on the graph and graph this thing, graph 350, and probably get rid of this one, and we should probably zoom to the stats and look for that intersection. And if it looks like it's going to happen off the screen, okay, we're going to have to zoom out a little bit. Now, I would caution you that in general, looking outside of the domain of the original data set can in general be risky. Sometimes that's what you got to do because that's what modeling is all about. Sometimes it's about extrapolating, and extrapolating is honestly far more useful than interpolating, even if sometimes extrapolating comes up wrong. So I'm going to go, instead of to 32.9, I'm going to go to x equals 100. We've got y equals 350 in there. So I think 100 would be good. I don't want the scale to be too crowded, so I just scale 10. Okay, and then, this will work. Okay, so we should be able to find an intersection point. So we will calculate where these two graphs intersect. Blue and red are intersecting. It looks near there. And we get x equals 47.056. So that would be the number of days it would take to surpass 350,000 downloads. So I would say t is approximately equal to 47.056. According to the model. Alright, this next one is talking about a football getting kicked. The height of the ball in meters was measured for selected times. Data is shown in the table above. Alright, and so based on the situation and the data presented in the table, I'm going to say, okay, well, the t intervals are equally spaced. It's all 0.4, so I will be able to, run a pretty nice analysis and say for each one, just kind of ignoring the fact that it's 0.4, or like the average rate of change I need to divide, I'm going to see a constant second difference in the table. So from 1.4 to 5.7 is an increase of 4.3, then 5.7 to 8.4 would be 2.7, 1.2, negative 1.2, 8.4 to 5.6. Oh, that's going to challenge me. Okay, that would be 2.6. That makes sense because I'm just one off from the other one. But no, 6 and 6 is not 4. That would be probably 2.8. Then 2.5 to 5.6 would be an increase in 3.1, so I'm going to be subtracting 3.1. All right, and if I look at the second order differences, that would be decreasing by 1.6. This would be decreasing by 1.5. Decreasing by, wait a minute, 2.4. Okay, that's interesting. Decreasing by 1.6 and decreasing by 1.3. Okay, we're seeing mostly constant second differences. That's a quadratic thing. And also the fact that the football is going up and then down, like, that's a quadratic shape, right? So I think that's going to be the most logical model. Quadratic because it goes up and down, or because we've got a constant second order difference. Find the appropriate regression function to model these data. I'm going to go to the stat menu and calculate a regression. It's going to be a quadratic regression, so I would choose option 5. I probably am going to want to store this regression equation into y1 because it looks like I'm going to need to, we're going to need to use it for something else. So I'm going to store that into y1, calculate, and get myself, okay, r squared is pretty okay. It's over 0.9, which I think means it's pretty good. Especially for like real world data. So I've got y equals a negative 4.606 x squared plus bx 12.858 x plus c is 0.288. That kind of makes sense. The ball starts off just a little bit above the ground, based on what we know about American football. And then using the model found in part B, what would be the predicted height of the football in meters at t equals 1.3 seconds. Okay, so that's just going to be h of 1.3 is approximately equal to y of 1.3. Let's see, h of 1.3 is approximately equal to what I would get in the calculator when I put that into y1. I've got y2 equaling 350. I don't really need to worry about that unless I, accidentally hit y2 here instead of y1, but that would be kind of hard to do, I think. So we're going to plug in 1.3 and let it run and say, all right, that's 9.219. Would be, they already said meters, but put that just in case. All right, now number 7, the federal funds rate is the targeted interest rate that commercial banks use when lending or borrowing money for each other, from or to. Federal funds rate changes the interest rate banks charge for loans and mortgages will also change. Yeah, the table above gives the federal funds rate in percent for selected times t, where t is the number of years since 2018. So R can be modeled by a cubic polynomial. Use a regression to write an equation. Okay, we're going to need to type in the data. So we go to stat, edit, and clear out these lists. Type in our data and ask for a cubic regression. So stat calculate cubic is 6, so I'm going to go over here. Looks like I'm going to need to do something else, so I'll store this in y1 and then I will ask it to calculate. Alright, I've got all this stuff ready, and then R can be modeled by a cubic polynomial. Yeah, write the equation. Let's just copy down our results. All right, and then based on the model we found here, what is the predicted federal funds rate for the year 2026? So I'm going to say like at the end of year 2026, or basically, okay, 2019 is 1 year since 2018, so I believe 2026 would be 8 years after 2018. Yes. Okay, so I'm going to just plug in x equals 8 or t equals 8 into the formula, and I would say, okay, r of 8 is going to be approximated by whatever this regression model gives me when I plug in 8. So y1 of 8 equals 52.357. Okay, that's probably not realistic. 52.357, and that would be percent like interest rate. And that's, yeah, okay. The highest federal fund rate in U.S. history was 20% in 80. Based on this information and the answer found in part B, do you think the cubic regression model found in part A is useful in predicting rates into the future? No. And also, let's see, the 8 and 5, 23. Yeah, okay, it had data for 2023, but you could probably even look it up and see that, like, right now, 2024 would have been y1 of 6. Let's actually think about that. Y1 of 6. It would be predicting a 13% interest rate. That has not come to pass. You know, happily or sadly for you, depending on whether you're a saver or a borrower. And so, no, like, the end behavior of the cubic is, pretty extreme. It's either plus or minus infinity depending on the nature of the cubic, and that's just not going to be realistic for this context here with like the finance. Okay, the last one we've got here is kind of a table problem, but there's just no table. So mass of bacteria in a petri dish is given by the continuous function p of t, where p is measured in grams and t is measured in hours since the start of an experiment. It's known that p of 0 equals 0.3, p of 3 is 2.7, and p of 6 equals 3.1. Or 31. Okay, based on the data presented, explain why an exponential model would seem appropriate. Okay, well, first of all, it's a bacteria in a petri dish, and that's kind of a classic exponential growth thing. But I think I've kind of got just like the last problem, I've got kind of a message on that. But, based on the actual data, if we laid it out as a table, we'd have T versus P. I think this would be useful. T equals 0, T equals 3, and T equals 6. I go from 0.3 to 2.7. So like about 0.3 to about 3. That's about multiplying by 10. Up to 3.1. When T increases by 3, I've again multiplied by about 10. Okay, so I would say, each time T increases by 3, P gets, increases by a factor of 10. Okay, just say that. And then use a exponential regression to find an equation that models P of T. So I'm going to just go to the lists. Okay, go to calculate an exponential regression, scroll up, that's option 0 on this one. I'm going to store my regression equation to y1, and then I will calculate. And I just kind of realized that I've every time called for Y1 out of the F4 menu, and I know that some people might be using a TI-83. I will one time, just remind you how to get that. I was very explicit in the original lesson video on that, on what to do if you have a TI-83. So I think you're probably all right if you were listening at all. And if not, hopefully you went back and looked at it. But I'm going to write down my regression equation now. So, okay, that's now on screen. So a times b to the x. So y equals 0.423 times b, which is 1.476. to the x. And, alright, Petri dish has a radius of 1 centimeter and a height of 1 centimeter. Density of the bacteria is 2 grams per cubic centimeter. Okay, so I'm taking it back to geometry a little bit. Alright, and, okay, I think it might look about like that. I might zoom out so you can see the rest of it. It might be just not going to happen. But pretty much the volume of this thing, I'm saying, is going to be the area of the base, so pi times radius squared multiplied by the height, because it is a prism. Okay, height of 1 centimeter, pi, radius squared, so volume is equal to pi. The density is 2 grams per cubic centimeter. This thing can only fit 2 pi, which is equal to 6.28 something grams of bacteria. Okay, and this exponential model is pretty soon going to go well beyond 6.28. For instance, let's just plug in, I don't know, we went to t equals 6. Let's plug in t equals 10 and see what happens. And give that a go. Yeah, already we are way beyond 6.28 grams. Okay, and so that's going to be, an issue. I think more realistically, we probably have logistic growth, but fortunately for us, logistic growth is not part of AP Pre-Cal. So that's just all I'm going to say, is that this Petri dish can only fit 6.28 grams of bacteria, yet an exponential model is going to keep growing forever, and so there's going to be at some point at which this exponential model clearly cannot be accurate. Okay, so that's all I've got to say for this example, and that's the last one for this video, so thanks for watching.